Let's take a look at oxidation and reduction as part of chemical reactions. Sometimes as part of a chemical change, electrons are being transferred from one element to another. This can be kept track of either by charge or by oxidation number. So oxidation numbers are a way of bookkeeping to see whether the element has any extra electrons or whether it is short some electrons. Oxidation refers to the loss of electrons, whereas reduction refers to a gain of electrons. So we have this mnemonic over here, oil rig. Oxidation is loss, reduction is gain. When we lose electrons and undergo oxidation, or an element that loses electrons or undergoes oxidation has an increase in oxidation number. If that element is an ion, you can see it pretty clearly by noting the increase in charge. So if you lose electrons, or if an element loses electrons, the charge is going to go up. So the charge is going to go up when you lose electrons because electrons are negative. If you gain electrons and undergo a reduction, then the charge is going to go down. And we're going to focus on the element undergoing oxidation or undergoing reduction. So we're going to focus on what's happening to that element. C and D point out that oxidation and reduction always occur in pairs. So if one element is undergoing oxidation, then it's effectively causing a reduction in the other element that's present in the reaction. So sometimes it could be referred to as a reducing agent. I just wanted to put C and D for completeness. We're going to focus on looking at things more the way that A and B and E and F are listing it. And I did mention before that oxidation and reduction are found in the other four types of reactions. Our previous lecture for 4.2 focused on double displacements like the precipitation reaction. So the other four types, the single displacement, combination, decomposition, and combustion, often have oxidation and reduction happening as part of them. All right, let's take a look at this example reaction. First, let's figure out what type of reaction it is. We have two things going to two things. One is an element and a compound, going to an element and a compound. So this is a single displacement reaction. And that's a type of reaction where you often find oxidation and reduction. This solid piece of zinc here has zero charge. So we have zinc with a zero charge over here. Hydrochloric acid dissolved in water separates, it's a strong acid, so it separates into hydrogen with a +1 charge and chloride with a -1 charge. On this side of the chemical equation, we have hydrogen gas, and hydrogen gas molecules have zero charge on them. And so each of the hydrogens in the molecule has zero charge. Then we have zinc chloride, which is an ionic compound. It's made up of zinc ions and chloride ions. So let's summarize what's happening to each of the elements in this reaction. For zinc, we have zinc with a zero charge on the left side of the arrow, going to zinc with a +2 charge on the right side of the arrow. The charge has gone up. That represents an oxidation or a loss of electrons. For zinc zero charge to go to zinc with a +2 charge, the zinc had to lose 2 electrons. So this represents oxidation, a loss of electrons. The hydrogen went from having a +1 charge to having a zero charge. In order to do this, it had to gain electrons. The charge went down, so this is a reduction. We have zinc undergoing oxidation and hydrogen undergoing reduction. In this particular reaction, the chlorine is not undergoing a change. It is -1 to begin with and -1 at the end. In that previous reaction, it was a little bit easier to see the electrons being gained or lost because there were charges on these elements. Sometimes it's a little bit more difficult to recognize the charge, and so we can use an oxidation number as a way to keep track of whether an element is short some electrons or has a few extra electrons, and whether that number of electrons is going up or down. So the oxidation number of an atom in an elemental state is 0. We saw that in the previous example where we had just zinc metal, solid zinc metal. The oxidation number and the charge, actually, of those zinc atoms is 0. Even if you have a diatomic molecule, some of the elements are diatomic molecules, these also have a 0 charge, and the oxidation number of these elements is 0. If you have an ion that is just monoatomic, so that means just one element in the ion, so for example zinc with a +2 charge, this represents zinc being short 2 electrons. This has an oxidation number of +2. If you have a polyatomic ion, that's when it gets a little bit more difficult to figure out the oxidation number. We have an example to practice down here. But for a monoatomic ion, we know that the charge is the same as the oxidation number. All right, so for hydrogen, we are going to count the oxidation number of hydrogen being +1 because we're going to be having it combined with nonmetals. We're not going to work with hydrogen having a -1 oxidation number this semester. So hydrogen we can count as having a +1 oxidation number. And oxygen we are going to count as having a -2 oxidation number. We won't worry about having any peroxides or superoxides this semester either. And then halogens are going to have -1 as their oxidation number. We need this step 3 because if we have a molecule, we might need to use hydrogen, oxygen, or halogens to figure out the oxidation number of something else that's combined with these elements. And there is a convention in chemistry that when you write the charge on an ion, you write the number first and then whether the charge is positive or negative, but the oxidation number you can write with the sign first and then the number. So that's just a little bit of a writing convention. I sometimes am writing it too fast and mix these up myself, but I thought I should point this out. So let's try assigning oxidation states to each element in the following substances. For this first bromine molecule, remember bromine molecules have a 0 charge. And so each bromine in this molecule has 0 as its oxidation number. So according to rule 1, the oxidation number of an atom in its elemental state would be 0. And for the same reason, calcium here, which is not written as an ion, this is calcium metal with 0 charge. Calcium would be 0 oxidation number for the same reason, because of rule number 1. All right, we do not have any monoatomic ions here listed, but we can look at this ionic compound and use rule 2 to get these oxidation numbers. Calcium chloride overall has a charge of 0, but within calcium chloride we have calcium ion and chloride ion. And the oxidation number of a calcium ion would be +2, and the oxidation number of a chloride ion would be -1, because these are monoatomic ions and so they equal the charge. The oxidation number equals the charge. All right, let's take a look at 3A and 3B to do our water molecule. So we are going to count hydrogen as being a +1 oxidation state and oxygen as being a -2 oxidation state. And let's take a look at how so far rule 4 is proving true. So the sum of oxidation numbers in the molecule would equal the charge on the molecule. So here for calcium chloride, we have an overall charge on the molecule, or we have an overall charge on the compound. It's not a molecule because it's ionic. We have an overall charge of the compound of 0. And if we add up all the oxidation numbers, one calcium with a +2, a chlorine with a -1, and another chlorine with a -1, we get a total of 0 for the oxidation numbers, and that equals the charge on calcium chloride. The same thing happens for water. We have hydrogen with a +1. Let's draw another hydrogen with a +1 because there are 2 of them, and oxygen with a -2. And so overall, the oxidation numbers add up to 0, which is equal to the charge on a water molecule. So Rule 4 definitely applies in these cases. Rule 4 can also be used to figure out other cases, like carbon dioxide and the carbonate ion. So the oxidation number of carbon plus the oxidation numbers of oxygen all have to add up to 0 because carbon dioxide has a 0 charge. So carbon plus oxygen equals 0 for the oxidation number, or for the sum of the oxidation numbers. Carbon we don't know, so I'll write that as C. Oxygen is -2, and this other oxygen is -2. We know that from 3b over here. So that gives us carbon -4 equals 0. And so carbon's oxidation number in this compound is a +4. So for carbon dioxide, the oxygens are -2 and the carbon is +4. Let's do the same thing for the carbonate ion. So this time all the oxidation numbers are going to add up to -2 because it has a charge of -2. So carbon plus oxygen plus oxygen plus oxygen equals -2. So we have carbon, -2, -2, -2 is -2. So this comes out to be carbon -6 equals a -2, which again brings us a compound where carbon is a +4. So for the carbonate ion, carbon is a +4 and the oxygens are each -2. Let's assign some oxidation numbers to the elements in these other compounds as well. It's sometimes helpful to break up an ionic compound into ions first. So potassium permanganate is made of a potassium ion and a permanganate ion. The potassium is relatively straightforward. It's a +1 because it matches the charge on that potassium ion. So in this compound, potassium has an oxidation number of +1. We also know that oxygen has an oxidation number of -2. And so now we just have to figure out what manganese has. So the permanganate ion has 1 manganese and 4 of the oxygen, and the sum of those oxidation numbers adds up to -1 because that is the charge. We don't know manganese, we'll just write that like Mn, but we do know the oxygen is -2, and that gives us manganese -8 being equal to a -1, which gives an oxidation number for manganese of a +7. So I will write that over here. So we have silver oxide. Again, oxygen is a -2. We can just kind of look at these ions here. So here we can see that oxygen is a -2 because that's the charge on the oxide ion. Silver is a +1 because that's a charge on the silver ion. And just like the charges add up to 0 on this compound, the oxidation numbers add up to 0 as well because they match. So let's take a look at sodium nitrite. We have sodium with a +1 charge, nitrite with a -1 charge. So we can see right away that the oxidation number on sodium is +1. The oxidation numbers of nitrogen and oxygen add up to -1. So nitrogen plus 2 times the oxidation number of oxygen would be -1. The oxidation number of oxygen is -2. And that gives us N minus 4 equals -1. And so our nitrogen would be a +3 oxidation number. And our oxygen would be -2. All right, let's get some practice identifying these reactions as either acid-base or oxidation-reduction. So acid-base, we have the transfer of a proton, which is a hydrogen ion. And oxidation-reduction, we have the transfer of an electron, which usually isn't written in the reaction. So what we're going to see is a charge or an oxidation number going up or down. Let me go ahead and separate some of these ions. So we do have a hydrogen ion in this reaction, and this looks a lot like some of those double displacement reactions we had earlier. That might be a good place to start actually, because we remember that acid-base is a type of double displacement. So when we're looking for acid-base, we're looking for a double displacement reaction. And if it's a double displacement where a hydrogen ion is one of the partners that's getting swapped, then that is a definite sign that we have an acid-base reaction, because we have a hydrogen ion being swapped from one compound to another. And that is the case here. We have hydrogen that was with the chloride, and it ends up with the hydroxide, making a water molecule. So this is a special kind of acid-base reaction where we have an acid and a base coming together to make a water molecule and a salt. So here we have our salt, here we have water. So the compound that originally had the hydrogen ion and gave it away is this HCl, which is hydrochloric acid. This is an acid. The compound that accepted the hydrogen ion, or the one that gained the hydrogen ion, is this hydroxide containing compound. So this is our base. So this is an acid-base reaction, a double displacement where one of the partners being swapped is this hydrogen ion. For this next reaction, we have two things going to two things, and we have a compound and an element going to a compound and an element. So this is a single displacement, and single displacement is one of those reactions where we frequently see oxidation reduction. A redox reaction is another name for a reaction where an oxidation and reduction are taking place. So let's go ahead and make a list of the oxidation numbers of the different elements on both sides of this reaction. So we have carbon, we have iron, and we have oxygen. Okay, so this compound over here is an ionic compound. So if we separate these into the ions, it should be apparent what the oxidation numbers are, because they'll be equal to the charges. And this compound over here is iron 3 oxide. We have iron with a +3, oxygen with a -2. So those are those oxidation numbers. This carbon is just in its elemental form. There's no charge. It's not sharing electrons with anything else. And so that has a 0 oxidation number. Over here we have an element iron by itself with no charge. So we have iron with a 0 oxidation state. Oxygen we have with a -2 oxidation state. And we did figure out carbon in carbon dioxide before, but let's go ahead and review that the carbon and 2 of the oxygen is going to add up to 0. The oxygen is -2, and so the carbon has to have an oxidation number of +4. So this is an oxidation reduction. We can see that the oxidation number of carbon is increasing, the oxidation number of iron is decreasing. Let's go ahead and summarize what that means. We have iron going from +3 to 0, and that is a decrease in oxidation number. That is a reduction. The iron is being reduced. And the carbon is going from 0 to +4. That's an increase in oxidation number. The carbon is being oxidized or undergoing oxidation. Okay, so over here, this equation, this chemical reaction, is a double displacement. We have two things, both compounds, swapping partners and going to two different compounds. One of the partners that is getting swapped is a hydrogen ion, so we definitely have an acid-base reaction. So this one is acid-base. We know because it is double displacement using hydrogen ion. This compound is the one that is giving up the hydrogen ion, so this is an acid. It's nitric acid, actually. This acetate is taking on the proton, so this is our base. It's accepting the proton. This particular acid-base reaction is not a neutralization like the first one was, because we don't have an acid and a base making a salt and water. But it is another acid-base reaction where a hydrogen ion is being transferred. I'll just make a note of that here, that this acid-base reaction is a neutralization because we have that acid and base going to become salt and water. This acid-base reaction is not a neutralization, but it still is an acid-base reaction. We're not covering acid and base reactions too much in this chapter because acid and base chemistry is a topic covered more in depth in Chemistry 102, but I just wanted to make sure that you know that an acid-base reaction is the transfer of a proton or a hydrogen ion. Okay, this last chemical reaction is an element and a compound going to an element and a compound. So this is a single displacement, which likely means that there is some oxidation and reduction going on. Let's make a list of all these oxidation numbers. All right, I listed all the elements that are on the left side. They are also on the right side. I wanted to point out that this sulfate ion is not changing over the course of this reaction. So we can figure out what the oxidation numbers for sulfate are, but they are not, those elements are not undergoing oxidation or reduction. But let's go ahead and do that for good practice. We have sulfur and 4 oxygens adding up to -2. Oxygen is a -2. So we have sulfur -8 being a -2 charge, which makes sulfur a +6 oxidation number. So we have +6 for sulfur on both sides of this equation and -2 for oxygen on both sides of this equation. Now let's take a closer look at magnesium and hydrogen. Here we have magnesium in its elemental form, so the oxidation number would be 0. Here we have hydrogen in its elemental form, so the oxidation number is 0. On this side of the equation, magnesium is an ion being paired with the sulfate anion, so the oxidation number of magnesium on this side of the equation is +2. Here we have each of the hydrogens being a +1 charge to be able to combine with the sulfate. And so on this side of the equation, hydrogen is a +1. So magnesium and hydrogen are the elements that are changing their oxidation numbers. Magnesium is going from 0 to +2, which is an oxidation, an increase in oxidation number. Hydrogen is going from +1 to 0, and so that is undergoing reduction because the oxidation number is going down. Since we are talking about oxidation and reduction as part of reactions this chapter, we are also going to learn how to balance an oxidation-reduction reaction, also called a redox reaction, by the half reaction method. And it's a little bit intimidating at first, but if you try a few, if you do some practice, it's kind of an interesting process. So we are going to separate a reaction. The first thing we're going to do is separate the reaction into two half reactions. One where it shows the element that is being oxidized, undergoing oxidation, and another where it focuses on the element that is undergoing reduction. Then the second step is to balance all elements except for hydrogen and oxygen. And then we have a third and a fourth step to balance oxygen and hydrogen. And then when we do that, we end up with a different amount of charges on each side of the equation. And so we need to balance the charge by adding electrons. We're going to add a certain number of electrons to whichever side is too positive to bring down the charge. Then the final reaction cannot have the electrons, and so we need to have the same amount of electrons in each half reaction, and we do that by multiplying a half reaction by 2 or by 3 if needed. Then once the electrons match, we can add the half reactions back together to get the full reaction. If your reaction is said to be in acid, you can skip step 8 and just go to step 9 and do a final check. If you have a reaction that is taking place in base, we cannot have hydrogen ions around if we are in basic solution. Basic solution means that there is very little hydrogen ion around. It's mostly hydroxide. And so we're going to be doing this extra step to add hydroxide to both sides. All right, this makes a little bit more sense if we are actually going through an example. So let's do that. So as we go through these examples, it might be helpful to have this list of steps next to you so you can keep track of what we're doing and follow along. This first example I put in here because I've often gotten the question, why do we go through this big process for balancing an equation? We already learned how to balance equations at the beginning of chapter 4. It didn't seem that bad. Why are we making this more complicated? And this equation, if you are just balancing the elements, we have 1 iron, 1 iron, 1 tin, 1 tin. So this looks by the elements as if it's already balanced. But if you look at the charges, this side has +2 and +4. We have a +6 altogether. This side has +3 and +2. We have +5 altogether. So even though this reaction is balanced as far as elements goes, it's balanced as far as atoms go, it's not balanced as far as electrons go. So let's see if we can modify this and balance this so that not only the elements are balanced, but the charge on both sides is balanced as well. And if the charge on both sides is balanced, that means the electrons are balanced. Okay, so we're separating this into two half reactions. This one's pretty straightforward because we have iron on one side. This is 1 half reaction. And we have tin on the other side. So 1 half reaction is going to focus on what's happening to iron. The other one is going to focus on what's happening to tin. And just to make the page less messy, I'm going to leave the states off for now. I'll put them back at the end, but it's just going to get too crowded. So I'm going to leave them off temporarily. Okay, so the first step is to balance the elements that are not hydrogen or oxygen. Iron is balanced, tin is balanced, so we're done. We're done with step 1 already. Okay, step 2 is to balance the oxygens by adding water molecules. That's not really necessary. We don't have any oxygen. We don't have any oxygen. It's already balanced. The next step is to balance hydrogen. Again, already done, already done. So then we're already on the 5th step, which is to balance the charge by adding electrons. So we have a +2 here and a +3 here. We need to add electrons to the side that is more positive. Okay, so if we add 1 electron to the right side, we'll have a +2 charge, which matches the +2 on the left. Here we need to add some electrons to the left side because that's more positive, and we need to add 2 of them because then the charge will add up to the +2 that is on the right. Okay, so the next step, step 6, is to multiply the half reactions if necessary to get the same number of electrons. And it is necessary because we have 2 electrons in this half reaction and only 1 electron in this half reaction. So we are going to multiply this reaction times 2, and that will give us 2 iron atoms, 2 iron plus 2 ions, going to 2 iron 3 ions, plus 2 electrons. Okay, so now we have 2 electrons and 2 electrons. We can add these back together. All right, so let's put everything that's on the left side of an arrow over here on the left side of this blue arrow. We have 2 iron 2 ions here. We have a tin 4 here, and we have 2 electrons. Now on the right side of the equation, here we have 2 iron 3 ions, 2 electrons, and a tin 2 ion. So we are going to simplify this, another part of step 7. So step 7 was to add the reactions together. We did that. Another part of step 7 is to simplify by eliminating things that are on both sides of the equation. And the electrons can therefore be eliminated. And what we end up with is that 2 iron 2 ions plus a tin 4 ion can make 2 iron 3 ions and a tin 2 ion. And step 9 is to do a final check to make sure that the elements are balanced and the charges are balanced. Our element iron 2 and 2, that looks good. Tin 1 and 1, that looks good. Total charge on this side, we have 2 +2s and a +4. That adds up to +8 on this side. Here we have 2 +3s and a +2, and that also adds up to +8. So we started with something that didn't add up charge-wise, and now we're ending up with something that does add up charge-wise. So this is our final balanced equation. Okay, let's try 2 more examples of balancing an oxidation-reduction reaction by the half reaction method. This first example, we didn't really have to go too much into balancing oxygen or hydrogen, so let's take a look at one of those. And this one is also going to be in acid, just like that first one. Then our last example is going to be in base, so we can do one that requires step 8. Our step 1 is to separate into half reactions. So let's go ahead and put copper on one side, and that is going to copper and sulfur. And on this side, we'll focus on what is happening to the nitrogen and oxygen. All right, so we have these separated. Step 2 is to balance all the elements except for hydrogen and oxygen. So copper is balanced 1 and 1, sulfur 1 and 1, nitrogen 1 and 1. Okay, that was all set. Now the next step is to balance oxygen by adding water molecules. This side does not have any oxygen, we don't have to worry about it. This side does have oxygen, and it's not balanced. We got 3 and 1. So we're going to have to add 2 water molecules to the right side of this equation to get the oxygens to balance. Now we have 3 oxygen atoms here and 1, 2, 3 oxygen atoms here. So we have the same amount of oxygen on both sides. Okay, now we have to balance hydrogen by adding H+ ions. We don't need any on the left half. This one, now we need some hydrogen ions. We have 4 hydrogens on the right side of this equation and nothing over here. So we need 4 hydrogen ions over here. Okay, so now we have our hydrogen balanced as well, 4 and 4. Now we need to balance the charge by adding electrons. This time we even need some assistance here in this half reaction. We have a +2 on the right, 0 charge on the left. So we need to add 2 electrons to the right side to get it to balance charge with the left. Here we have -1 and +4, so +3 on this side, 0 on this side, so we need to add electrons to the left. Okay, so that is step 5, balancing the charge by adding electrons. Step 6 says to multiply the half reactions if necessary to get the same number of electrons. And it's definitely going to be necessary because we have 2 electrons in this half reaction, 3 electrons in this half reaction. We're going to have to get them both to be the least common multiple of 6. We're going to have to triple this first half reaction, multiply that one times 3 so that we have 6 electrons here, and then double this one. So multiply this one times 2 so that we can have 6 electrons here and 6 electrons here. Okay, so we triple this whole equation and then we get 6 electrons there. And this one we've doubled, so 2 nitrates, 8 hydrogen ions, 6 electrons, so now we have a match, 2 nitric oxide, and 4 water. So now step 7, we can add the reactions together and then simplify what appears on both sides. So we're going to add the 3 copper 2 sulfide. That's the only thing on the left here. These things are also on the left here, so we'll put those on the left. So we've listed everything that appears on the left. Now we have to list everything that appears on the right. So on the right we have 3 copper 2 ions, 3 sulfur atoms, 6 electrons, 2 NO, and 4 water. These 6 electrons appear on both sides of the equation so they can cancel out. So I cleared some space. Let's go ahead and write the final answer here. And I'll include states this time. Okay, sorry it got a little crowded here, but 3 copper 2 sulfide and 2 nitrate ions and 8 hydrogen ions make 3 copper 2 ions, 3 sulfur, and 2 NO, and 4 water. This is supposed to be water over here. All right, let's do step 9, the final check to make sure that the elements and the charges are balanced. So we have 3 copper, 3 sulfur, 3 sulfur, 2 nitrogen, 2 nitrogen, 6 oxygen, 2 plus 4 makes 6 oxygen, 8 hydrogen, 8 hydrogen. So our elements are balanced. As far as the charges, we have 2 negative ones and 8 positive ones. So that's a positive 6 altogether. On this side, here we have 3 positive 2s, which makes a positive 6 on this side. So all of the elements all the different kinds of atoms, all the charges, all the electrons are balanced. So this is our final answer. Okay, let's do this last one here. And this one is in base, so we are going to use step 8. We have not yet seen that. So we got zinc as 1/2 reaction and some stuff happening to nitrogen as the other half reaction. All right, so for the zinc, there's no hydrogen here, there's no oxygen here. We're not going to have to worry about this side or this half for a few steps. This one will go through and balance the elements other than oxygen and hydrogen, which would be nitrogen. That looks okay. Now we have to balance oxygen by adding water. We need 3 oxygen, so we need 3 water molecules. Now we have to balance hydrogen. We have 6 hydrogen now. Oh, 6, 7, 8, 9. We have 9 hydrogen. So we are going to need 9 of those hydrogen ions here. Okay, so we got 9 hydrogens, 3 oxygens, and 1 nitrogen. All of our elements are balanced. Now it's time to balance charges, so we need to do both half reactions for that. We're going to have 2 electrons on the right side here to balance out this charge. Here we have a +9 and a -1 or +8 going to 0, so we need 8 electrons here. Okay, so now the next step is to multiply the half reactions if necessary to get the electrons to match, and that is necessary. We're going to have to multiply this equation by 4 so that we can have 8 electrons and match the other one. That gives us 4 zinc atoms going to 4 zinc ions and 8 electrons. Now that the electrons match, we can add them back together. On the left side we have 4 zinc, 9 hydrogens, a nitrate, and 8 electrons. Then on the right side we have 4 zinc ions and 8 electrons. And over here an ammonia and 3 waters. Okay, so now we come to step 8. If the reaction is in base, we need to add hydroxide to both sides because hydrogen ions do not exist in base. So we're going to go ahead and add 9 hydroxide ions to both sides of this equation. And when we add 9 hydroxide to 9 hydrogen, we get 9 waters. So here we have 4 zinc, 9 waters, a nitrate. Oh, I forgot to simplify by removing these 8 electrons. Let's just do that here. We don't have to copy them down again. We'll just cancel them. Okay. Now what we have is some water that appear on both sides of the equation. So here we have 9 on the left and 3 on the right. So if we take away 3 waters, that's going to make it simpler. All right, I'm going to start adding states because I think that we are close to being finished here. So 4 zinc solid atoms, 6 waters now, and a nitrate. And then here we have 4 zinc ions, 9 hydroxide ions, and ammonia. All right, let's just do our final check. Our elements, zinc 4, zinc 4, zinc is balanced. Hydrogen we have 12. Here we have also 12 because we have 9 here and 3 here. So we have 12 hydrogen here. Oxygen we have 6 and 3 makes 9. We have 9 oxygen here. And nitrogen we have 1 and 1. So our elements are balanced. Let's take a look at our charges. Here we have -1 altogether. -1 on this side. Here we have +8 and -9, which also makes -1. So we are balanced as far as electrons or charge is concerned as well. So that is step 9, our final check, and we are done with our last balancing by half reaction example.